So we're moving into a new chapter. The new chapter is entitled something like Energy and the First Law of Thermodynamics. Well, you can take a look at the topics, some through a chapter. You'll see, they're going to talk about mechanical energy, kinetic potential energy. They'll talk about work, integral FdX or F something, dz or something. Talk about power, the rate at which energy is transferred. Think about shaft as well as electrical. And then boundary work. We typically are interested in thermodynamics expansion of a gas trapped in a piston cylinder apparatus, and that's boundary work, integral PdV. And then we'll talk about heat transfer, energy balance for a closed system, open systems, next chapter. This chapter, everything's closed system, no mass transfer across the boundary of the system. And then we'll end with a discussion of cycles. Won't finish it today, but let's go ahead and get started. A lot of this, you already had a physics class. You already been exposed to it. Some of it near the end, it will be new. Finally, we're getting into some new material, but probably today there'll still be much of a review of what you've already been exposed to in your physics class as well as statics and dynamics classes. Define energy. It's like, hold it, this whole book is about energy, isn't it? We should have a pretty good definition of a term like energy if we're going to use it so much. But to find a real clear and crisp definition of energy is challenging. So I always ask for a volunteer, somebody who's not too shy in the crowd. Stick up your hand, I'll call on you, and you give me an engineer's definition of energy. There's got to be a really brave soul to embarrass themselves, because you know I'm going to tear your definition apart. No, I'll be kind to you. Go ahead. You're the first person to give me Einstein's, relativistic equals mc squared definition of energy. That may be an equation that has energy in it, but that doesn't define energy.
The vibration of atoms?
And a lot of times we think about energy on a molecular scale or atomic scale, and so things that have a lot of energy have a lot of vibration energy. On a molecular, they're traveling fast if they're ideal gases and then hit each other. Or if it's in a liquid or solid, they're vibrating and pushing against each other or pulling back and forth. That's a concept for internal energy, definitely. But a definition of energy. That's the classic definition that you got in high school physics, as well as probably your other physics classes. And that's a great definition of energy. You want to make a comment, Emmanuel? Please go ahead. And so most people would say the definition of energy is the ability of a system to do work. If a system has energy, it can do work. A lot of times you wake up, you're the system, you're hopping out of bed early in the morning, you say, I have a lot of energy, let me go do something, accomplish something useful. That's the concept. We're going to find that's a great definition of exergy next semester. Exergy. If you want to look ahead, look at chapter 7. There's a term called exergy. You can type into Google and use that as a dictionary or encyclopedia, and a lot of times you'll come up with pretty good definitions. So a physics definition, the property of the matter and radiation, it manifests as a capacity to perform work. Perform work. That's a very common definition. It's based on causing motion, especially or interaction on molecular level. That kind of internal energy is part of energy, a manifestation of energy. You can take a look at the origins of the word. Interesting. It's formed around the mid-16th century, and you come from French and Greek and Latin. But in this textbook, you're really challenged to find the nice, like, here's our definition of energy, and put it in italics and bold and offset in the middle of a paragraph or something. I didn't see it in this textbook. Did you? This book's all about energy. You would think that this book would have a great definition of energy, right? But it's really not in this book. Now, somebody says they found it somewhere in the 9 o'clock, and I couldn't find it with them, so keep looking and maybe we'll find it. So, first clicker question, right here. In mechanics, in the study of mechanics, energy is the capacity to A, B, C, D, or E. Let me go ahead and start this clicker, and we'll give you a minute. So, in the field of mechanics, what is energy defined as? We're down to 10 seconds. They're playing around. They might get caught. All right, so what is it? It's just like we talked about. In thermodynamics, energy is the capacity to, and now you have 30 seconds on that one. Look at all the answers. Cause a heat transfer, cause a work transfer, increase temperature, increase pressure, or produce a physical effect. What would be your best definition of thermodynamics? Energy. Thermodynamics. Did we talk about the etymology of this word? Heat, motion, burn, turn. So, thermodynamics is a study of heat and conversion. That's the origin into motion, okay? Burning something to turn something to do useful work, which was a novel concept before the 17th century. But so we have a generalized concept of energy. Mechanics is typically just I got speed, I have kinetic energy, I have elevation, I have potential energy, and we have the conservation of mechanical energy in systems. If you lose mechanical energy, where does it go? Thermal energy. Through viscous friction, dissipation, things like that. So the best answer for this, unfortunately, is to produce a physical effect. If you look at textbooks now, they really don't put that in. But if you look at an engine, listen up. If you go back and look at the engineering thermodynamics textbooks written in the 40s and 50s, they actually sit there and say, let's talk about energy. Let's clearly define energy. And let's struggle with it. And oh, by the way, this is the best definition of energy. A lot more at the 9 o'clock got this one correct. And the reason is I asked them, how'd you get it correct? Because I thought nobody would get it correct. And they said, well, there's 4 people here. Who is one of the 4 that would like to share their logic as to why that's the best answer of all the other answers? 4 people. I was intending to hit D. Come on, one of the 4. Who did it? Come on. I'm going to have to skip you. Yes, sir. Your friend is a friend. Your friend encouraged you to go to the wrong answer. That's okay. This is just all fun and games on this. Clickers are almost worthless as your overall point score. But if I put 0 on it, you know what? People just play. So it's no, I got like 3% of your overall grade to help you keep you honest. All right, now, nobody else wants to help me? This is what typically students say. Well, they think about energy as a generalized, broader concept than just mechanical energy, and then they think, oh, it's associated with that molecular activity, and it's temperature dependent, which is more than just speed and height. Hence, they think about, well, it can, more than heat transfer and work transfer by themselves, yes, you can increase temperature. If I have a lot of energy, I can make something hot or actually make it cold, but I can also increase its pressure and decrease its pressure if I have some energy. Hence, basically, the more general term is produce a physical effect. It seems like it can do something. If you have energy, you can do something. You can lift a weight, you can push something, you can make it hot or make it cold. So that's the more general definition of energy from a thermodynamic point of view. Kinetics. So kinetic energy, how many people remember from mechanics that the kinetic energy is 1/2 mv squared? How many people remember the gravitational potential energy is equal to mgz? Yeah. Let's go ahead and rederive these concepts. So introduce a coordinate system z, and z typically is called z because it's the axis the same direction, well, opposite direction of gravity as shown, so z going upward. We'll start with an object. That's our focus of our study, some mass. It's going at some speed, and let's put v1 shown in the direction of positive z. You could have a negative v1, or you could have it v1 is equal to 0, something. It could be positive, negative, or 0. The math will work itself out. And what forces do we have acting on this object if I have no external force applied to it? The only external force is due to gravity, and it gives me the weight. The weight. And the weight is acting downward, true? And it's equal to mg. So the magnitude of the weight is mg, and it's directed in the negative z direction. A couple seconds later, it has moved. And instead of being at the location z1, it's now at the location z2. And at that time, it has a different v. It has a different speed. Okay? But it has the same weight. And during the movement, it had the same weight. The weight's not a function of height, is it? Is the weight a function of height? No, it's just constant. So what you can do is you could sit down and say, I know one of the laws that I really studied a lot definitely applies. F equal ma. Name of that law? Newton's second law. And it's an observation. We have a lot of confidence in it. What is A? Acceleration. True? We're interested in acceleration in the z direction, in this case, not the x, just the z. So would that be the change in the velocity with respect to time? And can you see that the velocity you can think about being a function of time? True. But also, it's a function of location because location is a function of time. So we can think of v as a function of z, which is a function of t. So if by calculus, you could say, hey, I'm going to split this apart and kind of make it look like algebra's good. I'm going to put a dz right here and a dz right there. And so I can re-express the acceleration as the product of this term right here is simply v. And that term is dv dz. So the acceleration is equal to v times dv dz. You've seen that in your physics class. You've seen it in your other classes. It's a common strategy to do what I'm doing. I'm doing something that you've already seen. Okay? So we replace it. We say the only force acting is the weight mg, and it's in the downward direction. And that's equal to, because of Newton's second law, mass times the acceleration, which is v dv dz. And we're really interested in how v changes. So we have an ODE. Repeat after me. What is an ODE? Ordinary differential equation. I need one initial condition or boundary condition, something like that. So we'll say v at some z1 is equal to v1. And I'm good to go mathematically. Turn off my engineering concept, my engineering part of the brain, turn on the mathematician's part of the brain, and just do it. Do the math. Solve the ODE with that initial condition by what mathematical strategy? 2 words. Separate, integrate. That's it. So they put the minus mg dz, that's the separation part. Then we integrate. When you integrate, you say the m and the g are constants, and I'm going to just put the integral right here. It's really only integrating with respect to z. And then I have the m outside the integral there, and then the lower limit has to match, so I integrate from z1, where the velocity is v1, to the final z2 with the velocity v2. This way you put in your upper and lower limits, and you avoid that constant of integration. Fine. So I integrate, let's see, I have 2 integrals to do. This first one, which is on the left side of the equation, and this other one, which is on the right side of the equation. Which one's easier? On the left. I love that. Give it to me on the final. I want to see that integral on the final. So when you integrate it, I'm going to have to carry it over here. You pick up minus mg z2 minus z1. Do you agree? All right. Now the harder one on the right. We have the m times 1 half V2 squared minus V1 squared. True or false? So what we can do is we can put over on one side, we could put in 1 half mv1 squared plus mgz1 is equal to 1 half mv2 squared plus mgz2. So some concept comes out of this Newton's law. And in mechanics, we said, aha, we've discovered energy. And I'm going to call this first term kinetic energy, and this other term potential energy. And it's due to how fast it's going and how high it is in a gravitational field. And then we say, we have a conservation of energy statement, conservation of mechanical form of energy, saying that if I have this ball going up at a high speed, you know, it's going to translate that kinetic energy into potential energy. Or I could turn it around. I could have started with the ball at rest at high elevation and dropped it. And you have all solved those problems. So this is a review of that concept of mechanical energy. So what we'd have is we'd say the sum of the kinetic energy and the potential energy is constant. That's our simplest form of the energy statement that you've been exposed to already. You can solve a problem like this. We take an object. It has some mass. That's our focus of our study. Let's put a dashed line around it, emphasizing that's our control mass around that object called the mass. It starts at some elevation. It slides down without any air resistance and no friction between the mass and the ramp. It slides down a frictionless surface, and it ends up down here. And I think everybody in this room is capable of predicting the final speed at the end of the ramp. What principle would you use? Conservation of mechanical energy. True? So I skip that and leave it to you. Work. Ooh, we had conservation of mechanical energy, but now think of the concept of work, where I'm going to accelerate an object. For the introduction to work, often it's better to turn and go horizontal. So you have a coordinate system x. And we have an object. Here's my object. And here it is at a later time. It's easier to think about time. So it starts at location x1. It's going to end at location x2. It starts with speed b1. It ends with speed b2. See? How did that change? Gravity's not acting in the direction of x. And it's going to go on a frictionless surface, so there's nothing to, there's no friction here. This is frictionless. Okay? How are you going to change B1 different than B2? The only way is through a application of a F, force. True? So we go back to F equals MA, or in general, the sum of the forces equal to MA. In this case, we only have one force acting on the object. That's that F. I didn't describe it as a function of time or a function of position. We'll leave it general. And then we'll come over here and we'll do M is equal to V dx. The only difference is now I'm thinking of acceleration and velocity in the x direction instead of z direction, where before I was going up and down and called it z. Do you agree with that equation? Good. It's an ODE. I can have an initial condition. What's my mathematical strategy? Separate and integrate. Let's go ahead and do that. We have f dx equal to the integral of mv dv. What do we do with this term? Well, unless you tell me what f is doing over x, I can't compute that integral. I'm going to give a name to that integral. I'm going to give a name to that integral w. It's called work. Work is the integral f dx, that pushing work. We're later going to do cranking work, angular displacement instead of linear displacement, okay? But for linear displacement, I have integral f dx is called work by definition, integral f dx. And so what about the other side of the equation? You have m 1/2 b final squared minus b1 squared. So what we have is we have the work can cause a change in the kinetic energy. So the work, that's the external surroundings are applying a force, F, in the positive x direction on my system. My system is the mass, and it's going to make the mass, if F is actually pushing in that direction, make the mass go faster. It's going to increase its kinetic energy. True? Professor, will the math work if my object is already going fast and I apply a force in the opposite direction, like a drag force, to bring it to rest? Will the math work? Yes, it will. Yes, it will. But in that case, the work wouldn't be positive, would it? It would be a negative work. It would be a negative work, not into the mass to accelerate it, but to slow it down. So in general, we can turn it, and maybe in interest of time, I just allude to this. Introduce Z. Introduce, not only do we have the weight acting down, mg, but you have some other force acting up in the direction of increasing Z, Z1 to Z2. And the object at a later time is at a different location, Z2, this is Z1. And before it was traveling at V1, now it's traveling at V2. And you do the same thing, get an ODE, separate, integrate, defined work, and you find that the work is equal to the kinetic and potential energy at the end minus the kinetic and potential energy at the beginning. So somehow work increased the energy, or it could decrease the energy if it's in the opposite direction, right? And so what we have is the work into the system relates to a change in the kinetic energy plus a change in the potential energy. When you see this delta symbol right here, what does that indicate? I could put delta x. That means x final minus x initial. I could put delta h. That means h final minus h initial. Delta kinetic energy. That's the final kinetic energy minus the initial kinetic energy, okay? So that delta is shorthand for that change in the kinetic energy as well as change in potential energy. I want to consider now some other cases. I want to consider an object moving with aerodynamic drag. Think of a road, it's nice and flat. You're driving your car between here and Houston, you get out on the open road and you're just driving, open highway, right? You have a car, there's your car, and let's say you're not speeding, you're going the speed limit. V is the speed, and it's constant, and it's, 80 miles per hour. Okay? You're down the road. If you have no rolling resistance, all right, does the engine have to do any work to keep your car going down a level road, no rolling resistance, driving to Houston, or can you just sort of shut the engine off and coast to Houston once you get up to 80 miles an hour? Note, you have an aerodynamic drag force, FD from aerodynamics. True? All right. Now, this is a very simple concept. Your engine's going to have to produce a force to balance that. True? Through the drivetrain applied to the wheels. And so the engine will have to produce an equal and opposite force to keep it moving to compensate for the aerodynamic drag. True or false? All right. So think about this. We're at one location, x1. You come down here to another location, x2. What is the work done by the engine? Is the work done by the engine equal to the integral of the force that the engine applied times dx? Integral f dx? Where does that work go? It doesn't go into changing the kinetic energy of the object. It just goes into viscous dissipation and heats up the air around it. A little bit. A little bit. All right. What about power? Well, do this. Think about expressing this on a little change, a dx, and forget the integral. Just put a force that the engine produces times dx, and then I'm going to have a little bit of power that the engine has to produce. So for every little dx, like 1 foot, 1 inch, some distance that you're traveling as you're moving, you have some little bit of power or work that the engine has to put out. You take that equation, you have it in a small differential form, you divide by time, both sides, looks mathematically good. You look at this, the change in the position of the car as a function of time, that is known as the velocity of the car. And this is that force that the engine had to produce to compensate for the drag force, true? So we multiply those together, and this term right here is a W dot that the engine has to produce. What is that W dot? Power. So we have the concept of work, then work per unit time, known as power. This is all a review for you, true? Good. Now, how about a rotating shaft? Think about a shaft that's like this. And I'm going to rotate that shaft an angle. The angle is theta. What are typical SI units for an angle of rotation for a shaft? Radian. Radian. How many people, I wonder, don't know what a radian is in this room? Learn it. You've been exposed to it, right? A radian. Okay. Now, that angle of rotation, when you're rotating it, let's say there's a torque, tau, in that shaft. All right? Good SI unit for torque in a shaft. SI unit. That's a good USCS. Foot-pounds are great units, and a lot of the world still uses them. What is it in SI? Newton meter. Force times distance, or is it a force per unit distance? It's force times distance. All right. Now, what would be the work if I took that shaft and did a rotation? What would be a good equation? Would it be something like the cousin of the integral f dx, but it would be the work is equal to the integral, not force, but torque, d theta? Would that work? See the analogy? Yeah, that'll work. And then we said we want to move it now from work to power, so go to a differential form, a little bit of work equal to the torque times a small angle change, right? This is for a finite. This is for a very, very small infinitesimal change, right? That's the difference. And then once we have that, what do we divide by? Small change in time. And now what do we get for our power equation? We get that the power transmitted in the shaft is equal to the torque that's in the shaft times the rate of change of the angle. There's a symbol for that, Greek symbol, omega. Omega, omega. I know that my omega may look like a W, but that's an omega. So we'll do over here, this is, and what is omega, the name of omega? Angular velocity. That's right. Angular velocity. What would be the typical SI units for omega? A lot of times you draw it like that too on the shaft. It would be radians per second. I hate to say it, on a final exam not too long ago, I had rotation of a shaft and somebody needed to know the units of it, and I didn't give it to them, and I told the student, I'm sorry, you should have learned that in physics. Do the best you can on this final exam. Sit down and work on it. Because I know nothing during final exams. I know nothing during exams. I already covered that in the syllabus, right? So it's like, oh, professor, I can't remember what is the units for. I can't remember what a radian is. That's what the student actually asked. I think it's a radian per second, but I can't remember what a radian is. Please sit down and do the best you can. My office hours are not during the exam. All right. So all this hopefully looks like a good review for you. Let's press forward. We have electric current. Current can move energy. So think of two cases. One is either a motor or a resistor. Okay, just think even a resistor. You're just going to supply current coming in. We'll use the symbol I. I for current. What are the SI units for current? Ampere. Okay, it comes into a wire that's high voltage. It also goes out at a wire much lower voltage. So the difference in voltage we would call E. E is the electromotive force. It's the voltage. It's across the two wires. One has to supply and one has to return the current. True? That's how resistors work. That's how motors work. And so this was, I'm just going to call it EMF, electromotive force, in units of volts. Okay. So what happens is you can talk about work or you could talk about power. If you talked about work, you would probably want to talk about coulombs, like how much charge went across. That's so rare that we do that. So we really, when you talk electricity, you move right to power. You really don't talk a lot about work. If you wanted to, you'd get the power and then you would do a time integral to get the work, kind of backwards. But what is the power? W dot electric supplied either to the motor or to the resistor based on the knowledge of current and the voltage. That's right. The flow times the EMF, the electromotive force, the amps times volts. True or false? With confidence? Yes, it should be with confidence. And what units will come out of this one? Kilowatts, or watts, or something like that, right? But it's power. Somebody says, oh, if that's a resistor, this guy had a law. Ohm's law. What is Ohm's law? E equal to IR. So you could rewrite W dot as equal to not just I times E, but you could write it as I squared R or E squared over R. This is a good little review. Professor, let's just continue this whole semester this way. We just review stuff that we already know. I'd love it too, but we got to move on. Now, the other one, instead of a motor or a resistor, you could have what they call a battery. The battery has current coming out the high voltage and going in the low voltage to make the loop, right? And so here it's the same thing. It's just that the electric, W dot electric is not, if the battery is the system, this is out of the system, where if it was the motor or a resistor, this was power going into the system. So you got to be clear. What is my system? Oh, it's the motor. Electric power into the motor. Well, what's that doing once it gets there? Some of it makes the motor hot, and some of it makes the motor turn a shaft, right? Shaft power comes out of typically a motor. If it's an electric resistor, it's all just dissipated in form of heat. All right. Battery, oh, that supplies power out. Well, it's the same equation. It's I times E. Expansion of a gas. Well, what we are going to study ad nauseum is, this is a cylinder. We have a piston in it. That piston traps a certain amount of gas, and that's our system that we're studying in this piston cylinder apparatus. Is the piston part of the system? No, it's the surroundings. Our system is defined to be only the trapped gas. So as the gas expands, it's pushing back the piston, the face of the piston, it's pushing it back. It's expanding and pushing it back, right? So what would be expression for the work done? You can think about this net force, which is force per unit area, that concept. So this work would be the integral F dx. Oh, I like that from mechanics. Divide by A, multiplied by A. I didn't really change the equation, but now I have it for a gas where I have the integral of force per unit area is also the pressure, and the change in the area of the piston times the distance moved by the piston, the volume swept, dV. Professor, what is that V right here? Is this V velocity or volume? Does this book use different symbols for different V's? Not really. I wish it was, but they probably are just, you have to look at the context. Oh, that V is velocity, that V is volume. That's not too uncommon, okay? That you have to recycle symbols and just say, hey, that's what it is. So this boundary work for a gas trapped in a piston cylinder that may be expanding or being compressed is integral PdV. What would be the time rate? Well, this is rare. That's why I put an X in there. Rare, like this is rare. it's more common to talk about electric power and boundary work. But you could talk about boundary power as the rate of the gas expands. You just go del W is equal to P dV divided by dt, and you get W dot boundary work is equal to the P times the rate of change of the volume with respect to time. But that's rare. This is the big equation right here, okay, for work. Thermodynamic definition of work. I'm just going to read it to you. Work is done by a system on its surroundings if the sole effect on everything external to the system could have been the raising of a weight. It's an organized energy transfer. That's what a work is. Thermodynamic point of view. It's so organized that it could have resulted in, manifest itself as raising a weight in a gravitational field. That has the connotation of mechanical work. Mechanical concept of energy, whether it's either kinetic or potential energy. This may leave you a little cold, but that's out there in all the thermodynamic textbooks. Okay? It's like, huh? Does that make sense? Work is not a property. What's a property of a system? Temperature, pressure, volume, mass, weight, things like that. I could say, what is the temperature of this system right here? You say, oh, I think it's around 25 degrees C or whatever. What's the pressure? What's the volume? What's the mass? What's the work of this system? What? No, the system is going to have an interaction with the surroundings, and that's what work is. It's an energy transfer across the boundary of the system to the surroundings. Work is not a property. That's why I was taking that little thing to say this is dV, a small change in work, and this is del W, small change in the amount of work transferred. Did I say work or volume? Did I misspeak? Yeah, I misspoke there. Sorry. dV is a small change in volume. This is a small amount of work transfer or energy transfer by pushing or lifting or something like that. Okay? So the notation is very unique. That is a small d, script d. This is a small d as well. This is for properties. This is not for a property, but for a transfer. We use it for work as well as heat transfer, small amounts. Sign convention, because thermodynamics had its roots in, here's my system. I'm going to burn something to pump heat into the system. And that system is going to be a heat engine. And the purpose of that heat engine is convert as much of that heat into it into useful organized energy transfer known as work. You can't convert all of it. When we get to the second law, you'll find you have to dump some to the environment of that beautiful heat. But that's just what it is. It's limited energy transfer. You have to throw some of that energy out. So work out of the system is positive. That's our thermodynamic sign convention. We already talked about that work here. If the gas expands and our gas is our system, was the work out of the gas? Is that a positive work for this case right here? Is W greater than 0 for that case? The system is clearly the gas, and it's pushing back the face of the piston. It's doing work on the piston. Yes, it is positive. Compression of a gas. Is the work positive or is the work negative? It's negative. It's negative. The surroundings is doing work on the gas. So we do that infinitesimally small amount of work, uses that Greek delta lowercase d for a d, for a small interaction. I teach Thermo 2. Some students still don't know that. They're still like, I know it's hard. You're reading the book as you go along. Everybody's reading a book, right? You finished chapter 1, and you solved all the homework problems in chapter 1, plus about 10%, 20% more, and all the example problems. True? Now you're in chapter 2, and you're reading ahead of the instructor. So true. And you are, because guess what? If you fall behind in this class, it's hard to catch up. It's really hard to catch up. Okay, so don't fall behind. Polytropic process for next time. Thank you very much for your attention.